All right, good morning, everyone, and thanks for coming to the talk today. So today we're going to talk a bit about our approach to deep analysis of FHIR data at a very large scale. And then we're going to jump into a demo of doing so with some open source tools that we actually are making available as a Docker container as well that you can experiment with. We'll probably play with it upstairs a little bit after this talk. So I'm going to start with what I think, at least among this audience, is probably a fairly uncontroversial statement, and that is let's make all of FHIR data with consent available to the best available data science tools, the best available machine learning tools, simply because this sort of analysis, FHIR can be benefited from FHIR just in the same way that any application can be done from FHIR. So there's a tremendous upside if we can sort of close this gap between analytic tools and the value that FHIR provides. So that's probably not too controversial. So maybe I'll jump into something a little bit more controversial now. It says say, hey, the ultimate data science tool that everyone should use for all analysis should be Lotus 1-2-3 for specifically release 4 for DOS, and you have to go through your department to do an upgrade. There are people that have loved this tool, but okay, so maybe Lotus 1-2-3. I mean, it does have DataCube support and everything. Maybe it's a little bit dated, so we'll do something. Maybe R is the right tool for your workload, but maybe you want to do something in Python, so you're interested in scikit-learn or pandas. If this isn't quite the right thing, we have a lot of users that have big SAS installations, so if we want to do that. Several years ago, MapReduce was all the rage. So hey, let's build out machine learning algorithms that can compile down to MapReduce jobs in the Mahout project. And well, a little bit after that, this thing called Apache Spark came out, and for a bunch of analysis that could be done there. And then Google open sourced the Beam project, which has some really nice data processing properties as well that are being emulated by these projects. Or maybe all of this is just too much. You want something that provides a really nice complete in-a-box environment, and you want to do something like RapidMiner. So there's a lot of things. So this statement that I want to take all of FHIR and make it available to the best available data science tools is a pretty daunting task because there's not a lot of consensus on what those are. And even if there was consensus, even when there is consensus, for a specific tool, things change really quickly. So the fact is that we have to pick an approach. We have to pick a technology. But I think that it's very important, whatever path we do take, we need to hypothesis test it for change, with the realization that whatever we do now is maybe different even months from now, so we want to be able to evolve quickly. And the first step towards that is a very strong separation between our data sets and the tools that we're working with, and be able to iterate very quickly on the tools while leveraging the same data there. And if we're working in a data science environment, a lot of times you might see the data sets themselves just live as files in a file system. Then, I go to this directory and get that directory and get the other thing. One thing that we found in our analysis is that sort of file-based management for these data science workloads isn't sufficient. There's too many data sets, there's too much variance, there's too much complexity. So in there, we think it's really important to have some sort of standards-based data catalog. And of course, there's some good options there. We're going to show the open source option that we're using for that. But data cataloging, discoverability, and data management are as important as anything for this sort of data science workload. But even then, once we have all that in place, there's still a tremendous amount of complexity. So here's this is just the condition model that if we actually use this and we actually expand it out to a schema in our data processing system that I'll show. If you expand all the fields for just condition, it keeps going. And this is, great compared to what the world was like before. But I think this sort of illustrates the amount of intrinsic complexity in the analysis that we're trying to do. And the fact that these very large structures are difficult to use directly in a lot of analysis tools. So this gets to the next step. Once we have our catalog data, how do we make how do we deal with this intrinsic complexity of making it easy to use in popular machine learning tools? And I kind of think of that as an approach of, think of all this complexity as a shape in a very complicated shape in a very high dimensional space. And to start making use of that, to make that easier, we want to project that shape onto something that's much simpler, maybe just a table of data or something like that. Because all that complexity is necessary to represent all the use cases that consume it, but it's generally not all necessary to represent the specific use case that you're trying to tackle. And so the ability to take these very large complex data sets and then project them onto a simpler form and do so quickly and repeatedly and iteratively, because I may do a projection for all, say, lab values or something like that, and then realize, oh, I wanted to get some other values as well, or I wanted to change the code systems or the concepts that I'm using. The ability to quickly and iteratively create these new projections to satisfy the needs of the data science tools, I think, is a really important need, particularly when it comes down. Often these projections are just a simpler tabular form that meets those needs. And which kind of gives it to, frankly, I think this is some days the most concise description of my job. But it's there. Everyone wants giant spreadsheets. So how do we go about creating these projections? And I think that it's important to say that in a lot of these workloads, these data sets are growing and growing and growing from terabytes. I mean, we have several petabytes of data in some of our systems now. And we really want to be able to create these projections holistically, because it's not obvious what the right one is up front. So I want to be able to do it. I want to be able to manipulate it and work with it from there. And this kind of leads us towards a data lake style architecture, where we can bring in these data sets, we can land it in one place, and then by virtue of having these vast amounts of commodity processing power, we can create these projections interactively to create the views that I need for whatever analysis that are being done by hand. And so I think that's sort of the next key point I mean, we started with have a data catalog, project it from very complex data sets, and then a data lake style approach, I think, is an excellent way to work with this data for a lot of workloads. So what does our data lake look like? I mean, after all, this is a FHIR talk. And we really believe, I mean, that the structure definitions are the source of truth, and that all of our schemas, everything like that, should be driven from the FHIR structure definitions unambiguously and generated by them, so there's not a human sort of trying to re-implement them. And by that, we want the same FHIR data represented in our data lake as used as everywhere else. And by keeping things exactly the same, not just kind of the same or close to it, is really important. Because by keeping exactly the same data sets, well, the predictive models that we create are portable. If I do a machine learning exercise against this FHIR data, I can port it to anything that speaks FHIR potentially. Or if I'm building a cohort or doing some analysis or any research-driven thing, if I can do that directly against the FHIR data, then suddenly I can port that to other systems. And then similarly for research workloads, I mean, let's be honest, we have a reproducibility problem in a lot of research, and that we'll publish a paper, but then it's very difficult for others to recreate it. By attaching these standards, we can take a huge step forward in reproducibility and in ensuring that these things can be deployed in the systems. So if the structure definitions are our source of truth, if they're what we're hanging off of, how do we kind of close this? How do we make this happen? How do we implement such a system? Well, the one thing that's important to remember is that the FHIR structure definitions, they're a logical concept, and they're independent of the physical representation. So out of the box, there's JSON and XML that they heavily use. There's some RDF support that's less frequently used. We just saw a great talk by Patrick from Google on the protobuf representation of FHIR that's generated directly using this sort of similar approach, similar philosophy of, and we have our source of truth, and we want to generate an efficient data model that meets our needs from it. And in this talk, we're going to look at actually another representation of it using what's called the Parquet file format. So we don't actually natively go straight to Parquet. The system that we're looking at here actually uses Apache Spark for a lot of the analysis. But Spark sort of uses Parquet as its default preferred file format. So we actually get FHIR encoding in Parquet files with an exact one-to-one mapping of every single field in every single structure. And the reason for this distinction here is that there's formats like Parquet and a handful of others have some really interesting properties that can support a number of analysis workloads. So if you think about just like a giant store, a giant table of data, you might have a number of records and then a number of fields. And these fields, they may be nested structures as well. It's easier just to show them as atoms in this place, but they could be nested structures. And generally, when we store a collection of records out to disk, they're physically sorted in this way. They're in a row-wise format. So all the fields for a given record are physically stored next to one another. And if your predominant access pattern is to typically load most or all of each record, this is an efficient format, because I can just go get row 1, it's physically stored next to each other. For row 2, physically stored next to each other. So for a lot of workloads, row-wise is the best format, and which is why it's probably the most commonly used. For sort of the deep analysis or query workloads, there's some downsides to this, though. So let's say that field 1 is, say, the code values of observations, and I want to scan a billion code values from observations and only select a subset of them. Well, in this approach, what happens when we scan at the disk levels, I'll hit the first field, then I'll skip, and then I'll hit, or I hit A, then I'll skip along, then I'll hit D, then I'll skip a bunch of fields, then I'll hit G, then I'll skip a bunch of fields, and then so on and so forth. So we have a pretty inefficient scan mechanism. But what we can do is, by taking our FHIR resources and natively encoding them in a columnar format like Parquet, it looks like this. And so we're able to scan right down. And the user doesn't know. I mean, that's kind of the beautiful thing about this. It's still just FHIR. It's every single field. All the semantics are unchanged. We're just storing it in a columnar format so we can do really efficient queries. And we regularly do these sorts of things, where we're able to just run a Spark SQL query that hits billions of rows and comes back very quickly in single-digit seconds across the system. And that's sort of the core of the system that we'll jump into. So to support this, and we'll share links as well to the end of the talk, we've open sourced a project that we've called Bunsen that kind of picks off some of those, one of those technology choices that we looked at earlier with Apache Spark and FHIR as a way to do this analysis. And we're going to jump into Bunsen as part of the demo here. And I think I'd like also to call out as we go all the benefits that this project and similar projects have from the broader community. The demo here makes extensive use. Bunsen internally uses the FHIR APIs extensively to represent the data transformations, even though it's not on the surface. The demo we have here uses the Cynthia data set to produce everything there. And it's really great that this community is able to do these sorts of things together. So let's take a look. We'll jump into this system itself. So let me swap out. Now, I'll have a link to the actual demo at the end of this, so you can, and we can play with it upstairs. But ultimately, once you pull down the GitHub repository that's in the demo link, then we can basically just, once we pull that down, we can just launch the entire thing with just this Docker command. So I'm going to do kind of like a daring thing with regards to. I'm going to do a daring thing with regards to demos. It's like, not only is it a live demo, but I'm bootstrapping it from nothing. Just kind of show that yeah, we can do this too. Everything's available in the link. So if you want to experiment with it, all you need is Docker installed and then download the Git tutorial. So I'll go ahead and launch this. So if you're going to work through the demo or the tutorial yourself, you'll need to run through this getting started notebook first. In the interest of time and actually getting to the good stuff as part of this conversation, I've already run that here, so I'm going to go ahead and open up another notebook that demonstrates what we're working on. And I'll go ahead, and since we just actually launched the system from a complete standing start, I'm going to go ahead and run the first few cells, because just to give it a chance to bootstrap itself here. And so if all the demo gods are pleased there, everything comes up fine. All right, so what we have here, if you're not familiar with, this is an interactive online notebook. It uses a technology called Jupyter. It's pretty popular amongst the largest set of the data science crowd. There are a couple of alternatives to do it, to this sort of thing as well. But the idea is that this is live code within this notebook that I can enter and manipulate and work with it. And then as a result, whenever I execute the code, the output is displayed, in the cells below it. You'll see a couple things like two pandas here. Basically, what that does, it'll take the data and convert it into a pandas object, which is a Python library that is natively rendered in this toolkit. So the first cell is basically just setting up a local environment. So we're running actually an Apache Spark cluster. It's entirely embedded in this Docker container. So a little bit of ceremony to get that set up and just running locally. But in an actual production environment, you'll just get your Spark session and it'd be running on an arbitrarily large processing cluster. So for the next step is what we'll do here is that the getting starting notebook that I skipped over, it actually loads a bunch of data from Cynthia into a database here, where basically each FHIR resource, we're putting one table per FHIR resource. It's just a kind of a nice logical way to do it. And then, of course, our databases, we're just sort of logical grouping of tables so that we can explore them and use them in other ways. And so we're just kind of looking at, here's some of the content we have. Since this entire demo is packaged as a Git repository, we have a pretty small data set here, but there's enough that we can play around with a little bit. The next thing that I want to show in terms of this interactive analysis at scale is that value sets are so important in so many things that we do with FHIR that we found it really useful to add some sort of nice syntactic sugar. Actually, it's more than that. So it's nice semantics to this toolkit for value sets. So here, we're just kind of using some LOINC codes, but we can also, if there's established value sets, so for instance, in this demo, we're interested in things conditions that might indicate a value set of risks, conditions associated with diabetes, for instance. And there could be many of these. And here's just the example that's on the FHIR website that we pulled in as well. So these value sets can just be broadcast into our processing environment. And once they're broadcast, then we can write SQL natively against them. And the one thing that you'll find that sort of stands out as different is this in-value set user-defined function. So basically, I'm querying conditions where the code is in the CHD value set, which I just defined up here. So we can have a list of codes, or we can pull in an existing value set. We also have the ability to do like is a LOINC or is a SNOMED, so to walk anything that's a child in the hierarchy of those ontologies can be just plugged right into this. So if I run this, and again, we're live code here. So if I run this, I'm just limiting it to 10, and we've gotten this table out here. Now I think this is kind of neat, because actually here I was going to do this, but we'll go ahead and do something a little interesting here. Go ahead and add a cell just for fun. So this table is really simple, but if I'm going to do something like, let's say, park table condition, I'll run print schema here. And so basically, this will just load that condition table, and this will print the schema that was generated from the structure definition for a condition. So you can see everything in there. All the meta and everything is all mapped out. This is just using the base resource in this example, but we can generate it from arbitrary profiles or structure definitions as well. So everything is there. And I think this is an important aspect to this type of workload. Our users don't want some of the data. They don't want to call up and ask, hey, can you load this additional data set? They want everything with appropriate consent and security controls to simply be available for the analysis that they want to do. And so by doing this, everything in FHIR is simply there for analysis. But it's complicated, right? So back to that point earlier about how can we make it simpler to use? Well, I go in this half dozen lines of SQL, we've gone from the full condition model to I'm just interested in coronary heart disease and some code values that exist out of that. And just with this little bit of code, we can quickly go from that complex data set to something that's much simpler that I can apply analysis of more easily. So here's another example of I'm interested in, say, LDL observations. So I have another value set published there in 2017 in this system. So if I run that cell, kind of a similar. We're getting the values, we're getting the codes, we're getting the effective data of that. And this is sort of the pattern that I think that we're seeing emerge for doing this sort of deep analysis of complex data sets. We start with everything there, and then we just start creating, we think about the problem that we want to solve, and then we just start creating projections of that help solve that problem. So if I'm interested in this case, LDL values, I'll create a projection of that, and then I'll use that projection to solve the problem. And if I feel, something's not quite right, I throw this out and I create a new projection that better fits those needs. So and so once we have those, we can start doing some analysis of that. So we have the LDL values. We just want to get descriptive statistics of all the LDL values in this data lake. And so there's some nice built-in functionality. Once you're in a tabular form, we can easily tap into these sorts of things and see the min-max standard deviation and all that sort of thing. So here, and actually, it's a small data set, so this chart isn't particularly glamorous, but here we're just sort of charting the distribution of LDL values with this. In an actual bigger data set, you'd see a much smoother curve and that sort of thing. And once we have that understanding the data, then we kind of take the next step. So if I, for instance, want to build a cohort for some research study, we use this same pattern. We project everything onto data sets that fit our needs, and then we start using them. So in this case, let's say we want to build a simple cohort. I'm interested in people who have conditions related to diabetes, so diabetics or pre-diabetics or potentially other things, or they have an elevated HbA1c value. So we think that there's some diabetes risk there. So we want to identify these folks. And then we want to find all of them who haven't had a wellness visit in some period of time. So we can almost walk down the list of our cohort definition and create views of our data to support that. So the first thing that we'll do is we'll select from condition, and then we'll just use our diabetes risks value set, which you may recall is just a FHIR value set that we published towards the top of this notebook. So if I go ahead and run that view, so I got a list of people that have diabetes or pre-diabetes conditions based on the value set that's defined here. So and the nice thing is that while the entire creation of a cohort can be very complicated, this particular operation is actually pretty simple. I mean, I can look at this, I can tell if this data is right. If I want to, I can do statistical analysis, say, well, do I have way more or way fewer? So I can look at these pieces in isolation without having to try to hold all the complexity of a much larger, much more complicated system in my head at a given time. So if we do this, so this is our first table. This is our building block. Now, what's the next piece in our item? So we're interested in people with elevated hemoglobin A1c. Well, let's create another view of it. We're just kind of building our building blocks for defining the set of people we're interested in. So here we go again, same pattern in the value set for HbA1c. We want elevated ones, so we're just going to look if quantity.value is greater than what we expect, and we'll check status is final. And this is actually really kind of fun to do because like every single field, since it's unambiguously mapped to the FHIR structure definition, I just go to the website that defines the structure, and I just use that as the reference for writing the query with all the great documentation that goes along with it. So this is actually, I have to admit, I've had a lot of fun sort of playing with this thing just because everything's so well curated. And all of this data for this demo is generated by Cynthia as well. All right, so this is our list of people that have elevated HbA1c. Now what we can do is the requirements are interested in people who either have diabetes or that elevated HbA1c. So we can just union our data sets. So we'll take our high hemoglobin A1c and people with diabetes related conditions, and we can just union them together. And this creates that other view. And then we can do our analysis of this. Does this make sense? Are there people in that we don't expect? If there's something that's surprising, we can join back and figure out what went wrong with this set of data transformations. Next thing that we had is we wanted to find people who actually, right now we want to identify people. The requirements to identify people in this set who have not had wellness visits in the last 2 years. So the first thing that we'll do is we'll create our view of people who did have wellness visits. And then what we can do is we can simply do an anti-join between here's the folks that are at risk for diabetes, here's our wellness visits. We'll do an anti-join, which will only preserve the people who are at risk for diabetes but are not in the set of people who had wellness visits. And then we can run that and produce the cohort that we're working with. And the nice thing about using this sort of notebook experience is that we can take this, we can share it, we can save it off, and others can review it to make sure that these set of transformations are actually what we're looking for. And I think this leads us to another element, another sort of property of this analysis environment that we're working with, and that is immutable data sets are essential to it. Because reproducibility for this analysis, I mean, whether it's research or whether it's some reporting or whatever the use case is, to be able to run this exact same notebook and get the exact same results every single time is an essential property for a ton of workloads. the good news is that there's some really good patterns for doing so in a data lake environment. So what we tend to do is we tend to take our databases, so in this case our tutorial database, and we partition it by versions. So here's a complete view of the data that it looked like on January 1st, and here's the complete view that it looked like on January 8th, and so on. So I can basically say, I'm using this version of the data for my analysis, and then if I come back later, I can rerun this notebook, get the same result every single time. And reproducibility is, I think, an essential property, not just for research perspective, but just for a huge amount of data analysis that we like to do. So the next thing I was going to show here is that we've kind of done our sort of cohort identification. Now we want to jump into something maybe a little more interesting, in that a time series data plugs into an enormous number of tools for a bunch of analysis workloads, whether it's telling a patient's story, whether it's trending things over time, whether it's things like, or even machine learning workloads by creating this sort of ordered of events in time. So now we're going to go straight from those raw FHIR resources that we started with, and we're going to create a time series of data that work with it. Now these queries, they get a little bit more involved, as you can probably see here. But if you kind of zoom in and sort of read it from the inside out, it's actually fairly parsable. So in this case, I want to, for every unit of time, I'm interested in the average hemoglobin A1C, LDL, HDL, and triglycerides. So if I kind of look at, let's say we'll just look at the LDL here, because it's easier to say than hemoglobin A1C. So all I'm doing is like, I'm computing the average if the code value is in the value set of the LDL value set that we had here. So if it is, then I include the value quantity value in there. If not, I just return null, which has no effect. It's basically ignored by the aggregate function, the average aggregate function. And this is, these sort of nested if statements is actually in a lot of SQL dialects. It's actually standardized. It's something you don't see a ton of. The only thing that's specific to this system is this user-defined function to get that out. So we're just creating these aggregates, and averages or max, or we could grab mins or counts or really any aggregation function in SQL. From observation, we're scoping it to some period of time. And then since we want to, in this case, we're building a time series arbitrarily grouped on data for a month. So we're just grouping by the subject and the subject reference, the year and the month for that person. And then we'll go ahead and order it. So I actually have to run these first for it to produce output. So these ones are a little more involved. Run that. There it goes. So and again, straight from the conditions model, here's our piece of our time series data, actually for observations. And we can do the same thing for a bunch of different models, whatever we want to include in our time series. So here we're training lab values over time. The next one, let's detect the records of condition records that are reported for time. So it's exactly the same structure. So we're looking if there's hypertension, we include true. If not, false. And the semantics, at least in Spark SQL, of max is that true is greater than false. So this will return true if there's a hypertension condition recorded in that time frame. So if we run this thing, you can kind of, actually that one didn't print out because I just cached it and now printed it. But here, we'll go ahead and join these data sets together, where we'll grab some patient demographics, and we're going to join our patients to that observations table, to that conditions table, just using the year and month columns. And then we'll go ahead and run this. So there's our sort of simplistic time series of these data sets that we're working with. And you can see like the values there, and they're sort of loosely populated. So I might skip ahead just a little bit in the interest of time here. And then the nice thing is that these toolkits have some really nice statistical functions that we can just plug into on top of that. So once we have this time series here, if I want to, say, compute the correlation between LDL and triglycerides in this case, there's a built-in function to compute really a pretty rich set of standard statistical methods in this case. So here we'll do correlation. So if I run that between those two columns, and you can see in this data set, they're pretty strongly correlated. And then if you're familiar with windowing functions and statistical databases, those are all available as well. So for instance, if I want to add a column to our time series that indicates, hey, the person had a report of coronary heart disease in the next month, what we can do here is we'll simply window our data, partition it by the patient in order by year and month, and then basically the next window we'll just use the lead function, so it'll look a month ahead in our time series, and then add that month ahead to the current row, so we kind of have this nice tabular data. So this is a nice way to say, for a machine learning exercise, if I want to label rows, maybe I'll look n months ahead to determine if something happened in those subsequent months, and I can label those rows from there. And so it can kind of, if we run that, then you can see, and what this prints out, this adds our next month coronary heart disease column to this data set. So with that in mind, I was going to touch just briefly on the machine learning workloads in this type of environment. Now, we're at an interesting point here because deep learning is real and it's coming and it's exciting. I think there's tremendous potential there. And that said, I think that there's still a tremendous amount of benefit that can be gained from what is increasingly being called like a classical machine learning method. I mean, there's a ton of models being deployed today that could be improved, and many of these models are deployed in places that just don't have the infrastructure or the data availability to apply a deep learning technique. So there's a lot of space to be gained by the continual improvement of more of a classic machine learning algorithm, simply because hosting these models and serving them with sufficient data can be a challenge. As we asked earlier, just getting all that data to them is something that is probably going to take a little while to evolve to. So these classic ML algorithms still have a fair amount of life. And then the second piece of it is like even as we enter this world of deep learning where we're throwing hundreds of thousands of data elements at a model, and it's very effective in that, it's still likely that for some workloads, engineered features may provide value in that. So given enough data, a deep learning model can probably infer that all the different variations of hypertension are related, or that the lower intestine is part of the digestive tract. But it's likely that, at least in some cases, it might be effective to actually tell the model about these relationships by engineering features to complement the raw data that's passed into it. It's hard to say. It's probably going to be very use case specific. But I think that the key is like with all this stuff, is like we want to, if we optimize for anything, we optimize for fast iteration, we optimize for fast change in order to incorporate these things in these systems. And that's sort of one of our goals here, is to make all the data available so we can engineer features to support a variety of machine learning workloads while complementing other analysis that's going on. So with that, I'll skip back to the slide here. So some of the key takeaways that we've kind of put together in this is, we talked about earlier, a strong separation of data and tools, because things are going to evolve very quickly. Cataloging and data management of the data lake is as important as anything, because you can easily get lost in just the sheer amount of variety and different data sets you're working with. The ability to encode FHIR in an efficient columnar format creates these excellent performance characteristics, and using structured definitions as a point of truth. We reproduce from mutable data. And everything that I just showed through that demo, you can actually run yourself. It's on that Bunsen tutorial. I'm going to be upstairs a bit later and if anyone wants to come play with it and talk about it. Just have to run the Getting Started notebook first and launch it from there. And with that, that's all I had. So we have a few minutes for questions. Sarah. Yeah, so the question is the pipeline for getting data into the Parquet format in Spark. So the majority of our, so there's a couple things. So in the demo, what we do is the Bunsen library includes some ability that if you give it like a big directory or big dump of FHIR bundles, it'll take those bundles and it'll actually run a Spark job that takes them, and it actually takes them, it stores them in happy FHIR objects as POJOs, the happy POJOs. And then part of what Bunsen does is that it has what's called a Spark encoder that can take those POJOs and encode them natively in the Spark format, in the Spark data structure. And then once it's in a Spark data frame, then just Spark has native integration with Parquet, so we just do save as table or save as file, and a Parquet table comes out the other end. So really, we're just taking advantage of the fact that we're starting with Happy, we're encoding it in FHIR's native data model, and then we're starting with Happy, encoding with it Apache Spark's native data model, and then saving it out from there, and then at that point, it's a Parquet file. Well, yeah, so if you guys want to play with the demo, I'm going to be upstairs probably over the research table for later this afternoon. And otherwise, thanks a lot. I appreciate it.